In this video, we are going to solve question 6.48 and 6.49. Let us start with question 6.48. A block of mass 0.773 kilogram on a spring with spring constant 239.5 Newton per meter oscillates vertically with an amplitude of 0.551 meter. What is the speed of this block at a distance of 0.331 meter from the equilibrium position? So this is my equilibrium position right here. And amplitude A is the maximum displacement from the equilibrium position, which they have given to you as A equals 0.551 meter. This is the maximum displacement the mass can have. The mass of the block is 0.773 kilogram. And the spring constant for the spring is 239.5 Newton per meter. I need to find what is the speed of this block at a distance of 0.331 meter from the equilibrium position. So somewhere over here, between the equilibrium and the maximum height, at a distance of x equals 0.331 meter, I need to find what is the speed of the block. Now there is a simple rule to calculate the speed. And that rule is speed of the block at any position v is given as square root k over m a squared minus x squared. If you can remember, you can solve any problem with spring if they ask you to find speed at any particular point. Here k is the spring constant, m is the mass of the block, a is the amplitude, which is the maximum distance from the equilibrium position, and x is the position where you want to find the speed. So let's substitute here. V equals square root. Value of k is 239.5. Mass is 0.773. A is 0.551 squared minus 0.331 squared, which is your x. And when you solve this, you get the value of your speed as 7.7 meter per second. So this is the simplest way of solving a question like this. If you cannot remember this rule, you can always use the law of conservation of energy to solve this problem, which I'm going to show you now. So how to do the same problem using the law of conservation of energy? The law of conservation of energy says that total mechanical energy at any 2 points in motion will always be equal. So if I have motion here, point 1 and point 2, according to law of conservation of energy, total energy at 1 must be equal to total mechanical energy at 2. So this 2 point into consideration that we are going to take right now will be the point where I want to find my speed and the point with the maximum displacement. So you have 3 positions here: equilibrium, the point where we want to find the speed, and the point of maximum displacement. I'm going to use point 2 and point 3 to find my answer. So we can write total energy at 2 equals total mechanical energy at 3. We know total mechanical energy is sum of kinetic plus potential energy at those 2 points. So K3 plus U3. At point 2, since the block is in motion and it is neither at the equilibrium position nor at the maximum point, point 2 will have both kinetic plus potential energy. So kinetic energy we can write as half mv squared, and potential energy is, since this is spring, it's energy of the spring, half kx squared. At point 3, we are at the maximum height for the spring, the maximum displacement. If you are at the maximum displacement, here my velocity is 0. If velocity is 0, kinetic energy at this point will be 0. And total energy of the system will just be the potential energy of the system. So we write that potential energy as half k a squared. Same as half kx squared, but since here my displacement is the maximum displacement, in that maximum displacement we write as a, the amplitude. So instead of x, I'm writing here a. Now to find v, we can rearrange these terms, or you can substitute your values here and shift solve. You have everything you need to calculate v, and you can substitute the value here and shift solve. So let's rearrange. We can cancel off the halves here because it's present in every term on both sides of the equation. Then we are left with mv squared plus kx squared equals ka squared. Take this kx squared to the other side. Ka squared, since this was plus here, when you bring it to the other side, it becomes negative. K is common to both the terms here, so I will take k out. A squared minus x squared. Divide by m. K over m. A squared minus x squared. Take the square root to find your v. K over m. A squared minus x squared. When I use the law of conservation of energy, arrive at the same rule for velocity. I arrive at the same rule for speed as the one I used before. Then you can substitute your values to get the answer as 7.7 meter per second. So choose the way you want to solve. If you can remember this rule, you can directly use this to solve the problem. If you don't remember the rule, you can always use the law of conservation of energy to arrive at this rule. Question 6.49. A spring with K equals 10.0 Newton per centimeter is initially stretched 1 centimeter from its equilibrium length. Part A is asking you how much more energy is needed to furnish the spring 5 centimeter beyond its equilibrium length. So let's first start with part A. I will write down what is given to us. Question has given me spring constant K. K is 10 Newton per centimeter. Now this unit of K has centimeter. We need to convert this centimeter to meter. 1 centimeter is 10 to the power negative 2 meter. So to convert this to meter, I will write this K as 10. We keep the Newton as it is over. To convert this to meter, I will multiply it into the power negative 2 meter. When you solve this, you get your K as 1000 Newton per meter. Then the initial stretch of the spring, initially it is at this position at 1 centimeter. So I will write this initial stretch as x1, which is 1 centimeter. We will convert this to meter also. So divide by 100 and you will get x1 as 0.01 meter. Part A of the question is asking me how much more energy is needed to further stretch the spring 5 centimeter beyond its equilibrium length. So question is asking me how much more energy is needed when I stretch the spring from this position at 1 to 5 centimeter beyond the equilibrium point. So my x2, the final position, I will write it as 5 centimeter. which is 0.05 meter. The amount of energy needed to stretch the spring will be equal to the work done by the spring. So the more energy needed will be the extra work you do when you stretch the spring from 1 centimeter to 5 centimeter. So I can find that delta W as work done in stretching the spring at 5 centimeter minus work done in stretching the spring at 1 centimeter. Work done by the spring is half kx squared. So 4.2, I will write x2 squared minus half k x1 squared. So half and k are common to my terms. I will keep them out. X2 squared minus x1 squared. Now let's substitute. K is 1000. X2 is 0.05 squared. X1 is 0.01 squared. And when you solve this, you get your work done as 1.2 joule. So this is the extra energy required to stretch the spring from this initial position at 1 to a final position at 5. Now part B. Part B of the question is asking you, from this new position means this new position at 5, how much energy is needed to compress the spring to 5 centimeter shorter than its equilibrium position? Shorter means now we are going to compress it. In the first part, we were stretching the spring from 1 to 5. And when the spring arrived at 5 here, now when the spring is at 5, now we want to compress the spring from 5 to negative 5. Negative 5 means 5 centimeter from the equilibrium compressing. Since we are compressing it, we take a displacement from equilibrium position as negative. So now for part B, I can write the value. So now for part B, I can write my values minus I write my values x1 as 5 centimeter, which will be 0.05 meter, and x2 which will be minus 0.05 meter. The only reason we took it negative here because now we are compressing the spring. When you stretch the spring, x is taken as positive. Compressing it, we take it as negative. Now we use the same rule. The extra energy required will be equal to the change in the work done, delta W, W2 minus W1. So half k x2 squared minus half k x1 squared. Half and k I can take out, x2 squared minus x1 squared. So half times 1000. X2 and x1 are same values. The only difference is x2 is negative. When you take the square of a negative number, it is same as the square of the same number when it is positive. So negative 0.05 squared minus minus 0.05 squared will give you 0. So the amount of energy needed to compress the spring from 5 centimeters stretched to 5 centimeter compressed is 0 joule.